All right. I'd like to repeat two of previous lecture slide. These two slides explains the basic concept of resonant power converter, which is very important, extremely important for the remaining part of this lecture. So this is the schematic, simplified schematic of, it's called parallel loaded series resonant converter, but it has so many components. But first, think about this. This part inside of this box is gone and is directly connected to here, and this line is connected to here. All right? So this part is missing now. Okay? Then what we have is this voltage source and the SPDT switch, and this is the low pass filter. That is the structure of conventional PWM converter. So in the PWM conventional PWM converter, this part is missing. So this part is missing. Then we don't have this part. Okay? And the purpose of this picture is to show the difference between the PWM converter and resonant power converter. In the case of PWM converter, this pulse waveform generated by this voltage source and the SPDT switch is fed to the low pass filter, and the output of low pass filter is some waveform very similar to DC. So we converted one DC voltage to another voltage through this. So this is the PWM converter. So the difference between this PWM converter and resonant converter is simply presence of this part. Right? In this part, we have this structure. This is low pass filter structure. Okay, this part is remain the same as the previous, the PWM converter, but we have this additional part. In this structure, we have two low pass filters. Structure of this is low pass filter, and structure of this L, C, we don't have R. Okay, we don't have resistor, but functionally, we'll see this. I'll explain this later in detail. This part, seen this port, can be approximated as a resistor, one single resistor. Their distance is shown here. So this filter is LC. In parallel with this RD forms another low pass filter. So we have two low pass filters. What makes the difference is Q of this quality factor of this filter and this filter, they are way different. And this the parameter component value of this LC and this LC are way different. Right? These values are much larger than this. That means the resonant frequency of this low pass filter is much below than resonant frequency of this low pass filter. More important distinction is Q of this low pass filter is very low, typically less than 2, right? With small q, the frequency response of this low filter is something like this. So it only passes the low frequency component of spectrum of this spectrum of coming in waveforms, right? So it is low pass filter, okay? But if Q is increased, the Q produces this peaking at the resonant frequency. With large Q, this can be very high, right? Then in this part, in this low pass filter, the Q is very large, typically larger than 10 or 20. Then we have very peak at the resonant frequency, and we are making use of this part, right? So if the spectrum of harmonic of this waveform come into this part, that component will be magnified. All the other components will be attenuated a lot, okay? So this is called the frequency sensitive resonant band pass filter. The structure is the same as the low pass filter, but in its function, it is a high Q, very sharp, frequency sensitive, frequency selective band pass filter, right? So with this band pass filter, this is the frequency response curve of this resonant filter. So it has very high Q, high gain at this particular point, right? Suppose this is the waveform. we generate this pulse waveform in the same manner as the case of PWM converter, but switching frequency of this is very high. Okay, then we have the spectrum. Okay, only suppose the switching frequency is at this peak frequency of the bandpass filter, then only the fundamental component will pass through this bandpass filter, and the output of this scene here will be like this. Okay, so this is the fundamental component of this spectrum of these rectangular waveforms. So we have this, and other than this fundamental component, all the harmonic components are dead. Okay, they are not there. Then this waveform is rectified by this rectifier. Then you have this. Okay, this is the rectified version of this, and this signal is fed to the low pass filter, and low pass filter will take the average value of this, which is the output of the converter. All right. So we are achieving the same thing as the previous PWM converter, but process is different. All right. So we call it first step, DC-DC power conversion. First step is you convert this DC voltage to the pulse waveform using this SPDT switch. Okay. SPDT switch is combination of active switch. For example, this is a MOSFET and diode. Okay. This pair, combination of this active switch and diode is called the SPDT switch. Switching action of this will provide this, and this is fed to this high Q frequency selective resonant bandpass filter. Then only fundamental component will be passed through this, will be rectified. So first step is conversion of this voltage into a pulse waveform Vx, and second step is extraction of fundamental component of this waveform using resonant bandpass filter. And next, then we generate this VR waveforms. And next step is rectification of this waveform. And the final step is low pass filtering of this waveform. All right. Then you will have another DC value different from this. All right. Another important difference between PWM power conversion and the resonant one is the output voltage as well can be very complex. For the PWM converter, you have very simple relationship. Output voltage is duty ratio times input voltage. But in this case, the output voltage is proportional to the input voltage, but details about this is very complex. Right? It's not this type of curve, it's some strange curve. Okay. All right. Okay, we'll study this later in detail. And the biggest motivation of using this resonant power conversion technique is elimination of switching loss. Okay, so I explained this in the previous lecture, and let me go through the summary of that. This represents the active switch, probably MOSFET, but in practical active switch, there are many parasitic components. Typically for this MOSFET, it has this anti-parallel body diode. It comes with the structure of the MOSFET. If you have MOSFET, then you have body diode. You cannot separate them, or you cannot eliminate the body diode. So it is there, and it has some parasitic element. This is channel resistance, and this is parasitic inductance. And this is parasitic capacitance between gate and source terminal, COSS. There is another parasitic capacitance that's shown here is parasitic capacitance between gate and the drain, and the gate and the source, and the gate and drain. Okay, although there are three parasitic capacitance, but this one is the most important. Right? So this is the switching waveforms for the case of PWM converter. So switch is turned off before this line, and at this point, switch is turned on, or the channel is created with the threshold voltage level higher than threshold voltage at this point. Before turning on this switch is turned off, then this huge voltage of Vs is charged across this COSS. All right. So that is shown here, and the current through this switch is 0. Okay. When you create the channel, this current does not go immediately to the high value, and this voltage does not go immediately to this zero value either. Okay? Because of this parasitic component, there is some time delay. This voltage drops gradually in linear fashion, and at this point, channel is fully turned on. Before that, current is increasing slowly, like this. Okay? So in this period, this voltage and current is overlapping. They are overlapping. And if you have the voltage and current coexisting in some time period, then you have loss, product of them. So this area represents the loss during the turning on process. That's called the turn on loss. Okay? So that is the typical waveforms for the PWM converter. That kind of switching is called hard switching. Right? It's hard. I don't know why hard. Okay? Something is hard. Okay? Very difficult. All right. This is the case for the resonant converter. Due to the operational principle of this, if you select the switching frequency properly, before switch is turned on, this diode, body diode is turned on in advance. That means this diode is turned on, then this voltage across the capacitor, voltage stored in this capacitor is already discharged. So voltage here is practically zero before creating the channel. That situation is shown here. This is the VS, voltage across this drain and source, is reduced to zero, and you are creating the channel after this voltage is reduced to zero. Okay? Then current will increase gradually, but there is almost no overlap or very small overlap. That means the switching loss is almost eliminated or very attenuated, reduced. Okay? So that is the most prominent advantage of this resonant converter. It's called soft switching. More specifically, it is called zero voltage switching turn on. Okay, so you have the same explanation for the turning off, but it will come that point later. So I think this is enough for this for now. So with this, the switching loss is almost reduced. With that, we can increase the switching frequency. That reduces the size of the active component. That reduces the size of your converter. That will increase the power density of your converter. Okay, that is the biggest advantage of resonant conversion. And another big advantage is in this converter, circuit waveforms is almost sinusoidal for every current or every voltage. That reduces the EMI problem a lot. Okay, so this is another advantage. So with this, because of these advantages, people they prefer use this resonant power conversion especially for the high power application. Okay, so we are learning this. All right. How about the output regulation? So same as the PWM converter, we should have some mechanism that allows us to control the output voltage or to regulate the output voltage. Okay, so this shows the concept of this is something else. Okay, this is time domain and the frequency domain interpretation of this resonant power conversion, and the story about the output voltage regulation is coming next slide. Okay, so this is the time domain interpretation. With this is what happened here? Oh, okay, this one is okay. All right. So this is the pulse waveforms, and we have this bandpass filter here. And with this, we are just extracting the fundamental component of this spectrum. So we have this sinusoidal waveforms, and this waveform will be rectified and averaged to generate our voltage. Right? So in terms of frequency domain interpretation, this is the Fourier series expansion of this. So it has the DC component because this value is 0, and this is the VS. So actually, I forgot to put this DC blocking capacitor. DC value of DC blocking capacitor is much larger than this. So combination of this guy is doing nothing. It's just blocking the DC waveforms, right? So if this blocks the DC waveforms, then this is the Fourier series expansion of this, right? So this is pulse waveforms. If DC component is subtracted here, then this zero value will appear here, right? So we considered DC portion here, okay? So if this DC portion is removed, so we have zero line here, 0 volt line here, then this is what? This is odd function, all right? So odd function has only sine terms in Fourier series. So these are all the sine terms. Cosine term is missing. They didn't show up here. And with this zero voltage at the center of this waveform is called half-wave symmetry. Half-wave symmetry means this, okay, we are assuming this is 0 volt line is here because we considered this DC portion separately. That means this part is symmetrical, okay? So Ft plus T divided by 2 is minus Ft. This kind of relationship is called half-wave symmetry, okay? Simply means, so this part and this part is the same and the sign is opposite. Then you only have these odd harmonics, okay? So because of these waveforms, you have omega s, 3 omega s, and 5 omega s, so on, okay? Even harmonics are gone because of this half-wave symmetric feature of these waveforms, okay? So then with this, we have this is the fundamental component, third harmonic, fifth harmonic, right? And we have this filter, resonant bandpass filter. Suppose this is the 0 dB. This is 0 dB, right? But this doesn't matter because this part is gone by this. So we don't have this DC portion here. So we worry about this. And if you place the switching frequency of your component at this resonant frequency of this filter, then only the fundamental component will be magnified by this and this thing. Okay, maybe will be reduced a lot. Okay, this is the output spectrum, and I intended this one to be very small. Right? Then you recover this. This is the frequency domain, time domain representation, frequency domain representation. Right? This again explains the resonant power conversion in time domain interpretation. Another one is in frequency domain interpretation. Okay. Next one is output voltage regulation. All right. There should be a mechanism to control the output voltage, which is shown here. Right. So this is this waveform, pulse waveforms, and this is the frequency response of this resonant bandpass filter, like this. Right. So this is the magnitude of the gain at the omega s. It is shown here. And this is the fundamental component of these waveforms. Again, we need this blocking capacitor, and this is magnitude of fundamental component, and this is the gain of this transfer function at this frequency. So gain of bandpass filter at omega s, which is switching frequency, and sine omega st, we are only considering the fundamental harmonic of these waveforms. Okay, so this is the output voltage. This will be rectified, and to generate output voltage, so you have some value of output voltage. Now assume the input voltage of this guy is increased to Vs prime, so we have this much larger input voltage swing. Then you need to increase the switching frequency. So switching frequency has been increased. This magnitude increased, then this will be increased. Okay, then this is increased as well. So this fundamental component of pulse waveform gotta be increased. This is increased. Okay, larger than previous one, but now you increase the switching frequency. So switching frequency is moved from this omega s to higher frequency omega s prime, And because of this low pass filter characteristic of this band pass filter, this gain is reduced. So this gain will be reduced. Okay. Then control law of this thing is obvious. Control law is, this is fundamental magnitude of fundamental component of original waveforms, and this is band pass filter transfer function, magnitude of band pass transfer function of original case. Now this voltage fundamental component amplitude is increased by increase of this, then you increase this switching frequency, then this gain is decreased this much to compensate for the increase in this coefficient of the fundamental component. Okay? With this mechanism, with the negative feedback control, with some requirement, then our voltage will be regulated always in the steady state. Right? So that is the basic mechanism of regulating this resonant converter. So big difference compared to the PWM converter. PWM converter, you play with the duty ratio of the converter. Now you got to play with this switching frequency of your converter. So it's called frequency control. That is the basic control mechanism for this. There are another mechanism. You can modify the waveforms of these pulse waveforms, but that is the secondary option. So primary means of regulating this our voltage is frequency control, which is very, very troublesome for some case. Okay. All right. Let me show one example. This is called the full bridge LC resonant converter. So it has this structure. This is the full bridge structure. So you have two pairs of switch, and each pair is switched in complementary fashion. Okay. So when this Q1, Q2 are connected, so when Q1, Q2 switch are turned on simultaneously, then our voltage VT is Vs. Okay. Then now these two switches are turned off. This and the other diagonal elements are turned on. Then you have this negative Vs. So you generate pulse wave from here, like we did with the single SPT switch. You are using this bridge network to generate this, right? And by putting the switching frequency of this at the resonant frequency of this high Q band pass filter, the out voltage will be this sinusoidal wave corresponding to the fundamental frequency of these waveforms, and this waveform will be rectified like this, Vn, and the average value of this is Vo, this out voltage. Okay? So this is the basic waveforms. Nothing? We don't need that because there is no DC component here. Okay? We don't need that. And they should be in phase. Otherwise, I made a mistake. They should be in phase. We are assuming the resonant frequency located at exact resonant frequency should be in phase. How about the closed loop control? Closed loop control conceptually is the same as the previous PWM converter. We sense our voltage here and compare that sensed output to the reference voltage. This is the one we want to regulate at, right? Then with this condition, this magnitude of the G2 at DC divided by magnitude of G1 at DC, that ratio is infinitely large, then our voltage is always regulated at this value in the steady state. Okay? That is the basic regulation scheme of this converter. Right? And suppose somehow this our voltage is increased from the desired value, some reason. As I said, this goes to this negative sign, inverting terminal. Then this goes up, this control goes down, V con goes down. So suppose VO is increased, and control voltage goes down. Okay, but this the VCO has this relationship, this omega s switching frequency output of this VCO is inversely proportional to this. For this case, if this V con is decreased, then Vs is increased, right? Because it is inversely proportional. So this will be increased, right? So previously the switching frequency was somewhere here. Now switching frequency is reduced, increased to the higher frequency, omega s prime, but gain of this point is smaller than previous one. So then VR will be decreasing, then this will be decreasing, and output will be returned to the original value, hopefully, right? So this is the basic mechanism of frequency control. And the principle is the same as the previous PWM converter. Actually, the feedback mechanism of any power converter or any feedback control system is something similar to this. Right? So that is the end of section 1. And we move section 2. Right? Section 2. Here. In this section, we'll be talking about the RLC, series resonant tank, and the series resonant inverter. We'll be discussing inverter a lot. You are interested in converter, but there is a good reason why you are discussing inverter first, because the operational principle is almost the same in both the inverter and the converter. In converter, we only have output filter stage. And the frequency range of our interest at output stage is much lower than the tank stage. Okay? So this remaining part is very simple to analyze. So key is this inverter part. So we'll focus on this inverter first, then we'll move to the converter. Okay? So first, we need to review the resonant tank, resonant circuit, resonant frequency, characteristic impedance, quality factor, and so on. Okay. So first, let me introduce this circuit. This is called RLC, series resonant tank. So resonant circuit has at least one inductor and one capacitor. Right. Resonance is occurring between the L and C. So you should have L and C, one of each, or multiple of them, right? So there are so many variations of resonance circuit, but this is the simplest resonant circuit. It's called RLC. RLC, you have 3 components only, and they are connected in series. Okay, so to be a resonant circuit, we should have L and C. Okay, both of them, regardless of their numbers. And the reason we call it tank is why we call it tank. Tank circuit, tank network. Tank is storing something. Water tank stores the water, and oil tank stores the oil, and this tank stores what? It stores the energy, right? So it stores the energy. Maybe energy storage is one feature of this circuit. So we are using term tank. I like term tank, right? It signifies there's energy storage in it, right? And the resonance, there are so many different, seemingly different definitions about the resonance. I was thinking about this a lot, what is the resonance? And many books, they say different things. And you'll see resonance in this course, and you have seen the term, heard the term resonance in many other subjects, electronics or controls, okay? So there are so different interpretations about the resonance. So I went through several books, okay, and I picked one definition, and in that book, that particular books, it says the resonance occurs resonance across. We are talking about series resonance in here because this structure is in series and across at the frequency. So the frequency where the resonance, of course, we call it resonant frequency. At that frequency, the terminal current and terminal voltage is this. We assume this is the sinusoidal voltage. I'll use this, okay, let me call it Vs. I try to use two vertical bars here to signify the magnitude of this. But sometimes I'll be using something different. Okay, but I'll do my best to use this consistently. Okay, sine omega t, right? That means then is, this terminal current it has different magnitude. Okay, and they are same sine wave at the same frequency and without any phase delay. Okay, at the resonance, this terminal input voltage and terminal current, they are in phase. The terminal current and terminal voltage of tank network are in phase each other. That means what? This impedance of this becomes purely resistive or purely conductive. All right? That is the meaning of that. That means what? The reactance of this L and the reactance of this is completely cancelled. They are same in the magnitude, but they are out of phase. They cancelled. All right? That is the definition of the resonance. Okay? In this simple structure, we only have one L and one C, and this just the series connection. But really doesn't matter. You may have many things here, but at the resonance, the phase of this thing not the same, and they are purely sinusoidal at the same frequency. That is the definition of resonance adopted in that book. Okay, I was using different definitions past, but I like this one better. Okay, so it is written here. The terminal impedance or admittance becomes purely resistive or conductive. That means input impedance is R, or admittance is 1 over R, which is conductance G. Okay, that means if this case there is only one L, only one C, then the reactance of two components are cancelled perfectly. All right, but this concept can be applied to any other circuit configurations as long as they have L and C. Okay, more than 2. All right. Okay, and this is called series resonant tank, LLC. All right, resonant frequency is the frequency where the resonance occurs. With the resonance, this GI written here, this R plus SL plus 1 over SC. We replace S with J omega because we are talking about the sinusoidal response. Then we have this, and this one will be 0. Only R is remaining. Right? That means this is the impedance. Okay? So this reactance of inductor is here. Omega SL, and reactance of capacitor omega SC. Like this, they are same in magnitude and they are out of phase. So with this, then makes this one 0, and with this condition, this is called resonant frequency. Okay, this is the only one unique definition of resonant frequency. Right? So maybe some people use resonant frequency differently. Right? So I said that there should be a clear distinction between double pole frequency and resonant frequency. Right? So this is resonant frequency. Right? And another concept is this characteristic impedance GO is magnitude of the reactance component L or C at omega naught resonant frequency. Okay, so when you consider this inductor, this characteristic impedance is this. If you consider this capacitor, you have the same expression for the characteristic impedance. Dimension of this is impedance. This is L is impedance, and 1 over C is impedance. We have impedance squared, but we have square root in front, so dimension is impedance. Okay, so that is the reason why they call them it as characteristic impedance. Characteristic impedance is simply the reactance of L and C at the resonant frequency, which are cancelled, right? Okay. This is easy, right? And it's very interesting to have this situation. We have this RLC resonant circuit, RLC, and excited with this sinusoidal waveform at this resonant frequency, right? So this is a special case, but this is extremely important. So many concepts are developed from this setup. Right? Okay, so voltage drive, this RLC series resonance circuit should be excited by this voltage source, and each of these three components they works as the voltage divider. Okay, for the parallel resonance circuit, that parallel resonance circuit should be excited by current source, and parallel resonance circuit is sharing the current. Okay, they decide the ratio of the current at the node. Okay, but we don't deal with parallel resonant circuit in this class. Okay? Some people call it parallel resonant converter. That is not the true. What you call parallel resonant converter is actually that is the series resonant converter. The distinction is there is only one port, one path connected to the voltage source. Okay, then this voltage is divided by these three components. So that is the definition of the series resonance circuit. Now we are assuming the input voltage is Vm sine omega naught. Omega naught is resonant frequency. Okay, at the resonant frequency, reactance of this will be cancelled. So these are zero. They are surely connected directly at that particular frequency for that sinusoid at that particular frequency. So because this reactance of two reactive components completely cancel each other, then this voltage should be same as this voltage, and VR is same as this. So I draw this VR here, right? Then current through this R which is IR, which is IC, which is IL. They are all the same. There is only one path. It's given by this. This magnitude is Vm divided by R, which is this. Okay, and this current is going through this, right? Then how about the voltage here? So this is the basic equation for the capacitor. So capacitor should satisfy this equation, and if you performing this integration, you have this, right? That means this VCT is cosine waveforms, and with 90-degree phase. This is what? This is a phase delay, right? This waveform start here, and this waveform start here. So it has this 90-degree phase delay. Okay, so this is start later than this one. So it has 90-degree phase delay. Okay, let me. Okay, so you need to take a look at this point. The VCT start later than ILT, right? So this waveform. Okay. Think about the energy here at the previous circuit. All right. So we have same situation. This RLC series resonant tank is excited by these waveforms. Then this VRT is this one, which is same as this in voltage, right? So this is the voltage across this R. Then there should be a power dissipation at the R. Okay. So let's calculate that. So this is the E, energy dissipated at R. Okay. Not in the circuit. in R, which is the same as the total power dissipation in the circuit at R. Let's make it clear. And this is power. This part is power times this time is the energy, right? This is the energy dissipated in this R, okay? Maybe during one period. So this is the expression for this power, okay? via RMS, which is peak value divided by square root 2 squared R, and this T relationship with omega naught is this one. So we have this. This is a power dissipation in the circuit. All right. Then waveform of ILT is like this, and waveform of VCT is like this. If ILT is like this, then energy is stored in the inductor 1/2 Li squared. Okay, is the energy stored in the inductor, and 1/2 C VC squared is the energy stored in the capacitor. Right? At this point, the inductor is storing the maximum energy, and this capacitor is storing no energy. And the other way around, at this point, the capacitor is storing maximum energy, and inductor has no energy stored. Right? So the sum of these two energies are constant. Okay? E stored is at particular time moment, sum of energy stored in inductor and the energy stored in capacitor, some of them remain the same. Which one is this? Which one is this? Okay? The maximum energy stored in the capacitor is sum of energies in two elements summed at any time. Okay? With this condition is this. Right? Then think about this. This energy dissipated here is supported by input constantly. Right? So energy is supplied. This energy is supplied by source, and this LR, they are exchanging finite energy. They have different distribution. One goes to the maximum, the other one goes to 0. The other one goes to 0, and the other one goes to 0. Okay, something like that. All right. So I have noted here the dissipated energy is continuously supplied from the source, and two reactive components, they change energy losslessly. A finite energy is circulating between them. All right. Okay. So this is the basic feature of resonant conversion, resonant circuit. But this energy conversion is not directly related with the operational principle of resonant converter. Maybe it's this feature is related to the operational principle of resonant converter, but I cannot figure that out easily. Right? But this will happen, but this is remotely related to the principle of resonant conversion. Maybe I'll be wrong, okay? But that is my opinion. Okay? So don't pay too much attention on this. Okay? So this is the phenomenon occurring in the circuit. Okay? Okay, think about this. When Vs is disabled, this input source is shorted, then what will happen? This energy exchange in the sinusoidal fashion, the magnitude will be reduced slowly and until it vanishes. Right? So it is written here. When VST is disabled or input voltage shorted, all the waveforms oscillate, still oscillate, but the magnitude of oscillation will be reduced until it goes completely out of picture. Right? Okay? Think about this. First, you showed this, okay? Then this resonance, magnitude of resonance will go down, and suddenly you showed this. That means this magnitude of oscillation remains the same after that, and this oscillation will go forever. Of course, we are assuming everything is ideal. Okay? That is explained here. This is the situation. First, this switch 1 is connected to A here, right? Then it will show this sustained oscillation at constant amplitude of oscillation, right? And at this time instant, you swap the position of this then input is disabled, there's no energy influx in the system, then this will be reduced like this. It goes down, goes down. At this moment, you switch this connection from A prime to B prime, then there is no energy consumption here. Then this will go forever, like this. Right? So this is the conceptual illustration of this resonance. This is called damping. Right? And this is just graphical illustration of the switching action. So we are here, and at this instant, this switch is opened. Then we will have this, and at this point, switch is then this position, then it is visualized. Okay? All right. So now you understand the resonance. Another one, very confusing one, Q, quality factor. Right? Q is called quality factor. What is quality factor? Quality factor specifies quality of something. It specifies quality of the resonant tank as a energy storage. Right? If the quality of this energy storage, the resonant tank is good, then this Q will be high, and energy will be stored forever, right? So that is the definition of the Q. There are so many definitions of Q. You see the Q and the electronics, circuit theory, control, many other places. They are the same thing. They are the same thing. Okay? They don't explain the original definition of this. So they look different, sometimes very confusing, and sometimes in the control they use something else, zeta. Zeta is, they call it something else, okay? The relationship between Q and zeta is this. Q is 1/2 zeta, right? This, they call it damping ratio. Q is a quality factor, something like that. But there are only one definition for the quality factor, right? Quality factor is defined like this. This is the ratio between energy stored divided by energy dissipated, right? So high Q means this energy dissipation is very small. There is no energy dissipation. There is no resistive component in the circuit. This will be infinite, right? So we have some factor 2 pi somehow, all right? So let's calculate this. So energy stored in the circuit, we'll calculate this using the energy, in the previous slide, this is the energy stored, the inductor and the capacitor, some of them, okay, which is the same as the maximum energy stored in the inductor. This is energy dissipated at the low R, which is this, and we have a ratio of this, and we pre-multiply that ratio to 2 pi for some reason. The reason is to simplify the expression. Then if you cross out everything, you have this. Then you have this, and omega naught is 1 over square root LC, which is the resonant frequency. Then Q of this circuit is given by this. Right? So this is Q. It is derived from the original definition of quality factor of resonant circuit. Right? So this Q, high Q means it is very good energy storage. So this oscillation goes forever, right? If Q is infinity, if Q is large, it decays very slowly. If Q is small, it slow decays very fast. That's bad energy storage, right? So I have another illustration here. Okay, so switch is originally connected to A, and this switch is connected to A prime, right? No. Okay, A prime. Okay, so with this circuit will generate this, and now this switch is altered to the position B, then there is no energy coming in, there is no energy influx in the circuit, then energy will be dissipated, and the magnitude of oscillation will go down like this. This is the case for the R of 0.1, okay? Now, same thing happens here, okay? Then we moved this switch to here, okay? So it is connected to the B. We do same experiment with this R. It's 10 times larger than this. Then it decays very fast, okay? And we increase the R 10 times more, which is this. If this switch is connected here, and switch was connected here, and it goes like this, then it will decay very fast, like this. Okay? So Q, value of this is this, this is this. So this Q is very large. Okay? This is high Q case. This is low Q. Right? So this is the difference between high Q system and the low Q system in terms of the waveforms. Okay? Magnitude of oscillation. Okay. Now let's talk about the input impedance of LLC tank circuit. In here, we'll drive the input impedance with two different approaches, and we will compare the result of the two approaches. And we will come up with another expression about the Q. That expression is exactly the same as our previous derivation based on the original definition of the Q. Right? I showed. All right. So we are considering the input impedance of this. So this is an extremely simple circuit, but somehow I prefer this way. There are three circuit components, L, C, R, and each component has this impedance component. This is the impedance component of this L, right? So I should modify this. This is, C. This is asymptote of impedance of C, like this. And this is the impedance of R. Okay, so let me mark this. This is 1. R is number 1, and C is number 2, and L is number 3. Then we have this 1. Okay, no. 1 is this one, horizontal line. This is 1. And this is the 2, and this is 3, right? So this impedance is series connection of this, and we add this magnitude of impedance, 3 of them in series. First, we add this 1 and this is 2, right? One and 2. Then what we have is one and two. We take larger one. Then we have this. This is 1 plus 2. All right. So, and we have another component, which is 3. So 1 and 2 and 3. Okay. We take larger one because this is vector summation, and sum of two vectors will follow the larger one. Okay. So this final one. This is 1 and plus 2 plus 3. All right. So this is the asymptote of our input impedance, which is this. Okay. This is asymptote. Right. This is good. Right. Or how about this value at this resonant frequency? This value. Okay. This value, we have perfect cancellation between this L and C. Then at this particular frequency, GI is simply R. Okay? So it should go down to this point at the resonant frequency. All right? This is the plot of input impedance of this circuit. Right? It follows this and goes down to this. This is the R line here, goes to R and go back like this. Right? In terms of equation, so this part has this slope, which is this 1 over SC, is equation of this capacitor part. All right? At this resonant frequency, the slope changes from -1 to +1. -1 is minus 20 dB per decade slope, and +1 is 20 dB per decade slope. So you have two slope change from -1 to +1. There is a double pole. The double pole is here. So we have double pole equation. This is the standard form for the double pole equation. Okay? So this equation is constructed from this asymptotic plot of the magnitude, right? Still at this frequency, the magnitude of this input impedance should touch this minimum point of R. Right? That is so obvious at the resonant frequency. Reactance of this thing, they cancel each other. So the remaining is only R, right? So this is constructed asymptotic plot. Okay. All right. Then we compare the result of the two approach. Okay. One is based on the definition of the resonance, and the other one is we use the asymptotic plot of this transfer function. Right. So actual impedance near omega naught in the neighborhood of this resonant frequency, then we can evaluate the expression of the Q. Right. So we have this, right? So previously we went through this. This is the asymptotic plot of this combination of three circuit component, and expression of this is this, right? Based on this asymptotic construction, you have this, and magnitude of this at the resonant frequency. So we use J omega naught here, then this becomes -1, they cancel, so remaining is this. So only this omega naught C remains here, and 1 over Q is coming in the midterm, right? So this is in dB scale. So this omega naught is the resonant frequency. So omega naught is 1 over square root LC. Then it is the expression of characteristic impedance. We are talking about low scale. So this and this comes in the denominator. So you have a minus sign here. So this value in terms of dB scale, 20 log square root L divided by C minus 20 log Q. Right? That is derived from this asymptotic plot. Right? And you go back to the very beginning. Then the GI is combination of these three. Okay. Then they cancel at the resonant frequency. The remaining is R. Right? So maybe we call it number 1, equation number 1. And this equation number 2. Then by equating the equation number 1, equation number 2, which is this. Right? So this one, value at the resonant frequency is this one. It's same as this, and with this expression, we derive the expression for the Q, which is this, which is same as the previous example. Okay? In the previous example, we used the original definition of the ratio of energy stored and dissipated, and we have derived using the some circuit analysis technique. Let me delete this. This will confuse you. So we have same factor, same expression Q is the same as the previous case. All right? So all the Q defined in different textbooks, they are the same. They mean the same thing. Okay? The very original definition of is the ratio of energy stored and energy dissipated. Right? So this one. So this is the sketch of input impedance around the resonance. So this value is this is characteristic impedance, square root divided by L divided by C, which is this value. This is the minimum value of input impedance. Okay, it dips down to the 20 log Q, and distance between this is this is 20 log R, and this is the distance between this value, and this Q is this one. Okay, so this purple line is Q, case of This is Q of larger than 1, some number. Okay. Okay. So to conclude this discussion, so this input impedance business is rather important. All right. This is the GI characteristics. So this is GI. For the case of, so we are assuming this L and C, they are equal. Okay. Then with this, when R is 1, R is 1, Q is 1. Okay. So there is no peaking. And this is 0 dB. Right? Because this is 1. Because of the same thing. L and C, they are the same. And R is 1. So you have this. If you decrease R, then the Q is increased 10 times. And this value is 20 log R, which is minus 20 dB. If you further decrease R to this one, then you have minus 40 dB. Okay? So this magnitude dipping is expressed in as 20 log Q. So high Q means you have very deep dipping, sharp dipping. So we are talking about very high Q resonant tank in the resonant converter. Q value is typically larger than 10, less than 20, maybe 14, 15, something like that. All right? So this is the plot of impedance. And sometimes it's advantage to use the plot of admittance, which is a mirror image of this. Okay? You put upside down here, then this is the plot of admittance Y. So some case Y is easier to deal with than G. Okay? Many people, you are very accustomed to using the G, but some case Y is better. So this YI, which is inverse of GI. Okay? So that is the basic concept of resonance. In the tomorrow, we will discuss how this basic concept is related with the operation of resonant inverter. Okay? All right, I think this is it for today. Okay? Thank you.